So far we have derived 4 different Euler's equation for 4 different end conditions of the column, and we know that, or we learned that the equation of the columns for various end conditions are very similar in nature, which has a pi square ei term is there and L square term is there, and the denominator and numerator changes by factors of 2 and 4. And so that was a basic format of the Euler's equation. Now in this class we are going to discuss about the effective length of a column. So before moving into the effective length, the purpose of this particular concept of equivalent length is purely based upon a single equation, and that single equation is nothing but P is equal to pi square ei by Le square. So we are deducing all the equations to a single equation called as pi square ei by Le square. That means this particular equation pi square ei by Le square is applicable to all the equations. Now the question is, how can we relate the same equation, or how can we apply this particular same equation to all the different columns? So in order to do that, we have to define the equivalent length. So equivalent length is nothing but the length of an equivalent column whose end condition is a hinged one, and crippling load or the buckling load is same as that of the actual column. So don't get confused. We have learned 4 different end conditions: hinged, fixed free, fixed, and finally fixed hinged. And we have 4 different set of equations. But an equivalent column of a fixed free column is a hinged column itself. So basically an equivalent column is a hinged column, and this hinged column has the same crippling load as that of a fixed free column, or a fixed column, or a fixed hinged column. Now the question is, in order to have the same crippling load, what should be the length of the hinged column? So that's what is called as the equivalent length. Okay, so equivalent length of a given column with the given condition is the length of an equivalent column of same material, same cross section with hinged ends. So that is the highlighting point, hinged ends. So equivalent column has the end condition as hinged, and it has the same crippling load. The cross section does not change, the material does not change, the only thing that changes is the length. So that's how the equivalent length is defined. Now the question is, how can we relate different columns to this particular equivalent length? It's very simple, because we have the equation as equation for the crippling load for the hinged column as pi square ei by Le square. So if you take a hinged column, the equivalent column is same, hinged itself. So the length of the hinged column and the equivalent column are one of the same. Okay, so this is the equation for a hinged column. That's what's given here. Remember, both ends are hinged. The equivalent length of the column is equal to L itself for a hinged condition. Now we have to find what is the value of equivalent length for one end fixed, other end free column. So we will equate this to pi square ei by 4L square. So this was the equation for the fixed free column, right? Pi square ei by 4L square. So these two terms will get cancelled out. What is left with is 4L square is equal to Le square, and Le is equal to 2L. That means, in order to have an equivalent column for the fixed free condition, we need a hinged column with the length twice the length of the fixed free column. That is a physical meaning. That means, if you want an equivalent column for this condition, then the equivalent column is going to be a hinged column, a hinged column with double the end condition. So if this is L, this is going to be 2L. So these two will have the same crippling load P, same cross section and same material. So all these values 2L, L by 2, L by root 2 can be obtained easily by equating it with the equation. For example, if you equate pi square EI by LE square to 4 pi square EI by L square, what will happen? These terms will get cancelled out. We can say that LE square is equal to L square by 4 and LE is equal to L by 2. Right? That's what is obtained here. Similarly, you can obtain the value as L by root 2 for the one-ended fixed and other end hinged column. Now you no need to study all the big equations that we derived using the Euler's equation. Instead of that, you have to learn or by heart the equivalent length of the columns L, L2L, L by 2 and L by 2. That is very easy for you to memorize. That's what's the meaning. Now comes another important parameter, which is nothing but the slenderness ratio, which is defined as the ratio of what least length of the column to the least radius of gyration. That is LE by K. This is called as the slenderness ratio. LE by K is called. Now how come this particular ratio, slenderness ratio, comes into the picture? So if you take the equation P is equal to pi square EI by LE square, we know that I is equal to AK square. I told you that I has to be the least moment of inertia. So if you want the least moment of inertia, then it should be RK should be the least radius of gyration. So this is a general formula that we are going to use here. This is a general formula. When we solve the problems, we will use the conventional formulas like BDQ by 12, like that. We will go for that. But in general, I is stated like I is equal to AK square. And if you substitute it over here, we can say that P is equal to pi square E into A K square divided by LE square. And if we bring this K to the denominator, we can rewrite it as pi square E A divided by LE by K also. So this is going to be the slenderness ratio. So slenderness ratio is already there in your Euler's equation. That's what's the meaning of slenderness ratio, and this is a very important terminology, because this is how a column is being categorized. In the earlier lecture, I told you that the types of columns are based upon this particular slenderness ratio. Short column, long column, medium columns. They are purely based upon this slenderness ratio. Now, P is nothing but the crushing load, not the crushing load, crippling load or the buckling load, right? So, if I rewrite this equation, P is equal to pi square EA divided by LE by K the whole square, and if I take out this A and bring it to the left hand side, I can rewrite this equation as P by A equal to pi square E by LE by K the whole square. So this P by A is nothing but the stress. So in that way also you can rewrite this particular equation. Now let's see what is the this we have already told, because Euler's equation is pi square EI by LE square. This is purely based upon the considering the equivalent length of the column, and here PCR is the crippling load which is substituted in Newton. E is the Young's modulus of the column, LA is the effective length, and I is the least moment of inertia. That means when you have a cross section with you, you find out the value of IXX and IYY. Among these, choose the minimum value. Choose minimum I. That's how you have to solve the problem. So this particular topic, columns, this is an exception when we compare it with the previous topics that we have learned, because for all the other topics which included the term I, used the maximum value of I, but here we have an exception where we use only the minimum value of I. So when you learn this topic, this has to be marked in red lines, otherwise you will forget. You will consider everything as maximum, but here you have to consider the minimum, and I have explained the reasons in my previous lecture. Kindly go through that lecture and find out the reason for using the minimum value of I. Now usually this PC, PCR is the crippling load. This is usually the maximum load. This is usually called as the maximum load. This is not the safe load. In the question, sometimes they will ask you the safe load. But what you obtain using this Euler's equation is not the safe load, it's the maximum load, maximum crippling load. Now, if you are asked to find out the safe load, then you have to divide the PCR with the factor of safety. So, if factor of safety is not given, you have to assume it as 2, 2.5 like that. So, in the reverse order also, the question can come. Sometimes in the question, they will say that the safe load is 40 kilonewton and factor of safety is 2. Then you are not supposed to submit this 40 kilonewton over here, because that is wrong. You have to substitute the maximum value of the load. So in order to get the maximum value of load, you have to multiply this safe load with the factor of safety to get the actual crippling load. So this is a point where confusion can arise. So distinguish every term clearly and learn. Okay. Now, moving forward, we have to discuss about the limitations of Euler's equation. So, in this column, this particular topic is very, very important. What are the limitations of Euler's equation? Because this is repeatedly asked in many question papers. So, what are the limitations? See, if you look here, we can say that P is equal to pi square EI by LE square. And we have rewritten this particular equation like sigma is equal to pi square E divided by LE by K the whole square. So we said that this particular ratio is called as the slenderness ratio, right? Now what happens? See, if a column has a low value of slenderness ratio, what will happen? The stress will automatically increase. So they are inversely proportional. So as the slenderness ratio decreases, stress value increases. Now we derive the Euler's equation stating that all the columns should fail by buckling. Or that is what the main purpose of Euler's equation. Euler's equation says that this is the particular buckling load that is required for a buckling failure. Now, for a short columns, like if LE by K are very less, what will happen? This stress will go high, and what will happen is you can have a curve like this, right? So this is a sigma value, and this is the LE by K ratio. So as the LE by K ratio decreases, stress value increases. Suppose you have your crushing load here, and as the slenderness ratio decreases, what happens? Your crippling load, your crippling stress gradually approaches this particular value of crushing stress. Okay, and what happens? Once it reaches the crushing stress value, it fails by crushing. It doesn't fail by crippling. But this equation states that this is going to fail by buckling. But for the short columns, as the crippling load becomes equal to the crushing load, system fails by crushing, not by buckling. That means Euler's equation is not suitable for short columns. That is the first limitation of Euler's. And this is valid only up to the proportionality limit, and they are valid only for long columns, and it doesn't account for the direct compressive stress. This is nothing but the buckling stress. Here we have not considered the P by A here. That means direct compressive stress is P by A. This factor is not considered when we evaluate the stress in a material. So these are the limitations that an Euler's equation have when we discuss about the different types of columns. So short columns cannot be evaluated using this Euler's equation. Direct stresses are not considered. This is applicable only in proportionality limit, and these limitations are very much essential to design to understand the actual behavior of a column. Now, if you take the crushing stress of a column as 330 megapascal and Young's modulus as 210 gigapascal and slenderness ratio as 80, or not slenderness ratio is 80. If you use these two values and if you substitute over here, like 330 is equal to pi square into 210 into 10 power 3 divided by LE by K the whole square, the value of slenderness ratio you are going to get is 80. That means you cannot solve or design a column made using mild steel if its slenderness ratio is less than 80. So this is the limitation. So for any material you can have, you can calculate the limiting value of the slenderness ratio. So that has to be evaluated. So we need a better method to solve the columns which are subjected to compressive loads. So there comes the introduction of Rankine formula that I am going to explain in the next lecture. Okay, so in this lecture I have explained about the slenderness ratio, the equivalent length, and the limitations of Euler's equation. These three topics are very important. So kindly go through this and understand the concept properly. So thank you, and meet in the next lecture of Rankine formula. Thank you.